Welcome to the deep dive. Today we're jumping straight into a really fascinating area. It's where magnetism and topology kind of intersect.
That's right. In a specific material called MnB2T4.
Yeah.
Most people just call it MBT.
MBT, right. And it sounds complex, maybe, but the buzz is it holds real promise for future tech, particularly something called topological spintronics.
Exactly. And, to really get why MBT is exciting, you first need a basic idea about topological insulators, TIs.
Okay. TIs, what's the core concept there?
Well, imagine a material that's an insulator deep inside in its bulk, but on the surface, it conducts electricity perfectly.
So, like, electricity can only travel on the outside lane, a kind of electron superhighway on the
That's a
surface.
great way to put it, a superhighway, yeah. And inside, nothing flows.
How does that even happen? What makes the surface so special?
It comes down to a quantum effect.
Hmm.
Spin-orbit coupling. Basically, an electron's spin interacts with its motion around the atom.
Okay, spin-orbit coupling.
And this interaction fundamentally changes the material's energy bands near the surface, creating these special conducting states only there.
And these states are topologically protected, I've read. What does that mean in practice?
It means they're incredibly robust. Think of that highway again. It's like it has no potholes, no obstacles. The electrons flow without scattering off imperfections in the material.
Yeah.
It's a very efficient pathway.
That's pretty amazing. So that's a TI. Now, what happens when you add magnetism to the mix?
Well, magnetism messes with the key symmetry, time reversal symmetry.
Hmm.
Introducing it into a TI can actually open up a small energy gap in those perfect surface pathways.
Okay, so you break the perfect highway.
Sort of. You introduce a specific kind of gap, and this creates what we call a magnetic topological insulator. And here's where it gets really cool.
Go on.
Under the right conditions, these magnetic TIs can show something called the quantum anomalous Hall effect, or QAHE, which means you get quantized Hall conductivity.
Quantized, meaning it takes on exact, specific values based on fundamental constants.
Precisely. Like climbing stairs, not a ramp. The conductance locks on to multiples of a fundamental value, EPC. It's incredibly precise and robust against defects. That's huge for potential low-loss electronics.
Wow. Okay. So where does MBT fit into all this?
MBT is special because it's intrinsically magnetic. The magnetism isn't added later, it's built into its crystal structure from the start.
Ah, okay. So you don't have to, like, sprinkle magnetic atoms onto a normal TI and hope for the best.
Exactly. That's been a major challenge getting the magnetism uniform and strongly coupled. With MBT, the magnetic M atoms are part of the repeating unit. It simplifies things, potentially leading to cleaner effects.
That makes sense. And that brings us then to the study we're focusing on today. They used terahertz light.
Yes, terahertz spectroscopy,
Yeah.
or terahertz spec. And there's a good reason for that. That energy gap I mentioned, the one that opens up on the surface of magnetic MBT. Its size is right in the terahertz frequency range.
So terahertz light has just the right energy to see that gap and probe those topological states.
Perfectly put. It's the ideal tool. Remember, terahertz is very low energy light, much lower than visible light.
And the specific technique was time domain terahertz spectroscopy. What does that let them measure?
It lets them measure how the polarization of the terahertz light changes as it interacts with the MBT. Specifically, they look at Faraday rotation and Kerr rotation.
Okay, Faraday and Kerr rotation. Can you break those down a bit?
Sure. Think of polarized light like a wave shaking in just one direction, say, up and down. When this light goes through a magnetic material, like MBT in a magnetic field, that direction of shaking can get twisted. The amount of twist is the Faraday rotation.
Okay, twist going through. And Kerr.
Kerr rotation is the same idea, but for light that reflects off the surface. The twist happens upon reflection.
Got it. So measuring both gives you information about transmission and reflection.
Exactly. It provides a really comprehensive picture of the magneto-optical response. You'll learn how the material interacts with light under magnetism, both on the surface and slightly deeper.
Okay, so the goal of our deep dive is to really get into what this study found about MBT's magnetic states using this T-verse technique, and crucially, did they see signs of that quantized Hall state?
That's the core question. But first, maybe a bit more on MBT itself. Its structure's quite unique.
Right, it's a van der Waals material, layered, like graphene.
Similar idea, yes. Made of distinct layers held by weak van der Waals forces. You can imagine stacking sheets. But each MBT sheet is actually a stack of 7 atomic layers.
7. Wow. What's in there?
It's called a septuple layer, or SL. The sequence is tellurium, bismuth, tellurium, manganese, tellurium, bismuth, tellurium. Tibitium and tibite.
Okay, quite a sandwich. And the manganese, the M, that's where the magnetism comes from.
That's right. The amine atoms carry the magnetic moments. Within one septuple layer, these moments all point the same way ferromagnetically coupled, usually pointing out of the plane of the layer.
Okay, so each 7-layer unit is magnetic.
Yes, but here's the twist. When you stack these septuple layers, the magnetic direction flips between adjacent layers. Layer 1 points up, layer 2 points down, layer 3 points up, and so on.
Ah, so they alternate, like
Uh,
an antiferromagnet.
Precisely. It's called A-type antiferromagnetic ordering. Ferromagnetic within layers, antiferromagnetic between layers.
And that has consequences depending on how many layers you have.
Absolutely. If you have an even number of SLs, like 2, 4, or 6, the up and down magnetizations cancel out perfectly. Zero net magnetism.
But with an odd number, like 3, 5, or 7.
Then you have one uncompensated layer, leaving a net magnetic moment. It's called uncompensated antiferromagnetism, or sometimes ferromagnetism, depending on the details. It's layer-dependent magnetism.
That's really neat. And topologically, it relates to Bi2T3.
Yeah, Bi2T3 is sort of the non-magnetic parent compound. It's a well-known TI. MBT inherits that basic topological electronic structure from the Bi and T layers, but adds the crucial magnetic element with M.
Okay, so the theory predicted interesting things should happen when you shine T-Oindus light on MBT, especially in a magnetic field. What was missing before this study?
Well, there were strong predictions, but direct experimental verification of these specific Magneto-Terahertz effects, especially relating them clearly to the quantized Hall state, was limited. This study aimed to provide that direct quantitative evidence.
Makes sense. Fill the experimental gap. So how did they actually do it, the setup?
They needed very high-quality samples first. They grew thin films of MBT, just a few septuple layers thick, using molecular beam epitaxy, MBE.
MBE, that's the technique for growing almost perfect crystal layers atom by atom, right?
Exactly. Very precise control. They grew it on an aluminum oxide substrate. And because MBT can degrade in air, they put a thin protective cap layer of tellurium on top.
Smart, protecting the sample. And then the T-Hertz measurements.
Then they put these films into their time domain T-Hertz colorimetry setup. They cool it way down to about 3 Kelvin, just above absolute zero,
Why so cold?
to minimize thermal noise and make the quantum effects clear. And they apply a strong magnetic field up to 6 Tesla, perpendicular to the film.
Okay, cold temperatures, strong magnetic field, and then they shine the T-Hertz pulse.
Right. They send in a polarized T-Hertz pulse, and then they measure the polarization of the light that comes through, for Faraday, and the light that reflects back at different times, for Kerr.
How do they separate the transmitted signal from the reflected one if it's all happening fast?
That's the time domain part. The initial pulse goes straight through that gives the Faraday rotation, but some light reflects inside the substrate and comes out a bit later. This first echo pulse contains information about the Kerr rotation from the MBT substrate interface.
Ah, clever. Using the timing of the echoes, like sonar, almost.
Kind of, yeah. It lets them disentangle the different signals.
Yep.
And their T-Hertz source covered the 0.4 to 1.6 T-Hertz range.
Which, as you said, matches the expected energy gap size. Okay, let's get to the results. What did they see for the 6 septuple layer film?
Right, the 6SL film. Remember, even layers, so it should be antiferromagnetic with zero net moment at zero field.
Okay.
And indeed, at low magnetic fields, below about 1 Tesla, they measured basically zero Faraday rotation, just as expected for the AFM state.
Makes sense. The opposing layers cancel. What happened as they increased the field?
Between roughly 2 and 4 Tesla, things changed. They saw a clear, finite Faraday rotation emerge, and it depended on the field strength and the T-Hertz test frequency.
What is that signal?
This indicates a transition to what's called a canted antiferromagnetic state, or CAF. The magnetic moments in the layers are no longer perfectly anti-aligned. The external field starts to pull them, making them tilt or cant slightly towards the field direction.
So they're not fully aligned, but not perfectly opposed either. Like they're leaning.
Exactly. This canting means the cancellation isn't perfect anymore, leading to a small net magnetization, which causes the Faraday rotation. For example, at 3 Tesla, 0.4 terahertz, it was about 1.6 milliradians.
Okay, so AFM state, then this canted state. What about at even higher fields?
Above about 4 or 5 Tesla, the Faraday rotation started to level off. It saturated. It didn't increase much more as they went up to 6 Tesla.
Saturation, meaning?
Meaning the magnetic moments in all the layers had basically fully aligned with the strong external field. The material entered a ferromagnetic FM state.
Forced into alignment by the strong field. And what were the Faraday rotation values there? Close to the theoretical quantized value.
Remarkably close. At zero point 0.4 terahertz, it reached about 3.1 milliradians at 5 Tesla and maybe 3.2 at 6 Tesla. The theoretical prediction for quantization in this limit is around 3.5 milliradian.
Wow, that is close. So very suggestive of a quantized effect.
Extremely suggestive, yes.
What about the Kerr rotation, the reflection? Did it follow a similar pattern?
Broadly, yes. For the 6SL film, Kerr rotation was 0 at 0 field, again, as expected for the AFM state. As they increased the field, a Kerr signal appeared. Interestingly, it showed frequency dependence. It was generally larger at lower tier's frequencies.
And at the highest field, 6 Tesla.
It reached its maximum value, around 8.5 milliradians at the lowest frequencies measured.
And the theoretical prediction for quantized Kerr?
That's expected to be around 10.5 milliradians. So again, in the right ballpark.
Still pretty close, though. Why the small differences from the exact theoretical values for both Faraday and Kerr?
The researchers point out that the theoretical quantized values are typically calculated for DC, meaning zero frequency. Their measurements are at terahertz frequencies, which are low but not zero. So some deviation is actually expected. It doesn't invalidate the conclusion of near quantization.
Okay, that makes sense. So they see these near quantized optical rotations. How does that connect directly back to the quantized Hall conductance, the QAHE state?
Great question. They use their Faraday rotation data, BCF, to calculate the terahertz Hall conductance, GHC. There's a known formula that relates the two, involving fundamental constants and the substrate properties.
Ah, so they could extract the conductance from the optical measurement. What did that calculation show?
He showed a beautiful three-stage behavior mirroring the magnetic transitions. At low fields in the AFM state, the calculated GHC was essentially zero. In the intermediate canted AFM state, 2-4 key, GHC became finite, but was clearly below the expected quantized value.
Right.
But then at high fields, 5T and above, where they saw the saturated Faraday rotation, the calculated GHC also saturated, right around 0.9 times EE.
0.9 emitter. That's incredibly close to the magic value of 1 ILF4 for the Chern insulator state.
Exactly. Remember, E pool is the fundamental quantum of conductance. Seeing it saturate so close to 1 times, that value is considered really strong evidence that the system has entered the Chern insulator phase, the state exhibiting the quantum anomalous Hall effect.
So the T-Hertz optical measurements provide a way to witness the electrical quantization.
Precisely. It's a contactless probe of that quantized Hall state. Yeah. Really robust evidence for the topological nature of this high-field ferromagnetic state in the 6SL film.
That's a fantastic result. Did they check the 7SL film too? That one should be different at 0 field, right? Oddly.
Yes, they did. And they observed similar overall trends in the Faraday and Kerr rotations as a function of magnetic field, because it starts with a net moment. The low field behavior is different, but the high field state is key.
And the calculated Hall conductance for the 7SL film at high field?
Also very close to quantization. Under 6 Tesla at 0.4 terahertz, they calculated GHC to be around 0.86 ELOT for the 7SL film. Again, very near that 1 ELO value.
So it seems consistent across both even and odd layer counts once you push it into the ferromagnetic state with a strong field.
That's the takeaway.
Okay, let's try to summarize the key findings then. Using this time domain TOS spectroscopy on these carefully grown MBT thin films.
Both 6 and 7 septuple layers.
Right. They observed magnetic field-driven transitions from AFM to canted AFM to FM.
Yes, and crucially in that high field SM state, the Faraday and Kerr rotations approach values very close to those predicted for a quantized system.
And translating that Faraday rotation into Hall conductance showed a saturation near the quantized value of EOA.
Which is strong evidence for realizing the Chern insulator state, this quantum anomalous Hall state, in MBT using terahertz light as a probe.
So, stepping back, what's the bigger picture significance here? Why is this study important?
Well, it really solidifies our understanding of how topology and this intrinsic magnetism play together in MBT. Seeing these quantized effects so clearly at terahertz frequencies is, well, it's beautiful physics, confirming theoretical ideas.
And beyond the fundamental physics applications.
That's the long-term hope. Demonstrating this kind of precise quantum control in a material like MBT is a vital step towards potentially realizing those futuristic topological spintronic devices.
Devices that could use these dissipationless edge states for ultra-low power electronics, perhaps, or new kinds of magnetic memory?
Exactly, things like that. We're still a way off from commercial devices, of course, but experimentally verifying these fundamental quantum phenomena in promising materials like MBT is absolutely crucial progress. It shows the potential is real.
It really is amazing probing these incredibly subtle quantum states with terahertz light.
Yeah, it's a powerful technique meeting a fascinating material system.
So maybe a final thought for our listeners. Given these results, these quantized Magneto-Terahertz effects, what kinds of maybe unexpected technological innovations could materials like MBT eventually enable? Where might this intersection of quantum physics and material science lead us down the road?
That's a great question to ponder. What new device concepts might become possible when you can control these quantum states so precisely with light and magnetism? Definitely food for thought.